Welcome to 20th lecture in mechanics of materials. The last class we solved an example problem of a simply supported beam subjected to uniformly distributed load. We want to analyze this simply supported beam. Okay. So, we solve the governing equation d square mg by dx square equal to minus w with the boundary condition that the moment at the hinge end and the roller end has to be 0 to get the bending moment as w by 2 into Lx minus x square. Okay. And then we got the shear force from differentiating the bending moment with respect to x to get this particular variation in here. And then to get the deflected shape of the beam, we solved the governing equation got from the beam bending equation that d square delta y by dx square is given by mg by E times Izz to get the with along with the condition that at the hinge and roller end the vertical deflections have to be 0 to get this expression for the displacement of the beam as a function of x. Okay. We plotted this and we plotted how does the angle change, that is the slope of this function with respect to x. Okay. What we know already from the bending equation is the bending normal stress sigma xx is related to the bending moment through this equation mg by Izz into y, okay, wherein the variation of this stress is a linear function of y. So, it varies linearly like this, the top phase in compression and bottom phase in tension, because mg is negative. Okay. You will get I left a negative sign here because, and you will get this as top phase being compression and bottom phase being in tension from this equation in here. Okay. Now, what we are interested is, we are interested in finding what the shear stress is, that is sigma xy. In particular, we want to show that the shear stress varies parabolically with its maximum value being in the neutral axis location. Okay. We want to relate the shear stress distribution to the shear force, because the shear force is what arises because of the shear stress. Okay. If you recollect, we have seen that the sigma xy dA is nothing but Vy. From the previous two lectures we saw this, that Vy is given by this expression there. Okay. So, now to understand why the sigma xy arises, let us look at a small demonstration. I have these two rubber blocks which are not connected to each other. Okay. Now, let me say I bend it by applying a non-uniform load. I am bending it by applying a non-uniform load. See what happens at the edges. You can see what happens at the edges. The edges are not flat, the plane sections are not remaining plane. There is a shift in the white line, and you can see that at this edge there is a zigzag nature of the plane there. Okay. The plane is not remaining smooth. This because at this interface, since it has not been glued together, there is no mechanism to resist the shear stress that comes at that interface, and the shear stress is maximum at that interface because that will be the neutral axis of this cross section. Okay. So, basically because of this there is a jaggedness in the cross section. The assumption that we made in the analysis that the plane sections remain plane are not holding good. On the other hand, if I take a glued rubber blocks same size, but it has been glued here, you can see I can't separate them out, you can see I can't separate them out. So, now let us say what happens if I bend it, let us say what happens if I bend it. The straight line remains straight, the edges remain parallel here, they are not going zigzag because the glue is resisting the shear stress that is developing at that interface, and hence it is able to do this, and this one is much stiffer to bend compared to the other block which is much flexible. Okay. So, now we saw the importance of shear stress in the bending action, and hence we want to be able to compute the shear stress so that we can design the structures appropriately for the shear stress if they have to resist the shear stress. Okay. As we saw here, if I have a non-uniform bending moment, what happens is the axial stress that develops at this phase and at this phase will be different, because the bending moment is varying from here to here. Okay. Since the bending moment is varying from year to year, if I cut any one half of the beam, this half was in pure compression when I bend it together, and hence what happens is this net total compressive force acting at this section should be balanced because the bending moment is varying here. For that it has to develop a shear stress at this interface. Okay. The shear stress developed at this interface has to be countered by a complementary shear stress, which we saw from moment equilibrium has to be same as this shear stress developed here, should be in equilibrium. For equilibrium, moment equilibrium, there should be a complementary shear stress developed at this face. Okay. So, that is what we are going to do. We are going to do this calculation systematically now. Okay. So, basically what we have is we have a beam subjected to some arbitrary loading, and I am interested in segmenting this beam at two sections like this with the distance of delta x, a small sectioning along the axis of the beam. If you recollect, as usual we are assuming that this is the x axis, this is the y axis, and this is the z axis. Now, apart from sectioning along the vertical along a line parallel to the y axis, I want to section it along a line parallel to x axis also like this. Okay. I want to section it like this. Let us assume that this distance is some y, arbitrary distance y, and let us assume that this distance is some arbitrary distance x. Okay. Now, I want to draw the free body diagram of this cut section. This cut section I am drawing it here. Okay. So, basically what I have is I have this vertical lines cut here, then I have the blue line cut here. Okay. And there is some loading acting on top. Okay. Since this is some distance apart and I am assuming that the beam is bending like this, there will be compression on the top face. So, let us assume that this is sigma xx at x. Okay. And similarly there will be some compressive stresses acting on this face, which is sigma xx at x plus delta x. Okay. The magnitude of sigma xx at x and x plus delta x will won't be same because bending moment is varying along the length of the beam. Okay. Therefore, sigma xx at x should be given by, from our bending equation, it will be mz at x by izz into y minus y naught. Okay. And similarly, sigma xx at x plus delta x will be given by mz at x plus delta x divided by izz into y minus y naught. Okay. Now, what happens? I know I can write mz at x plus delta x using Taylor series as mz of x plus dmz by dx delta of x plus higher order terms of delta x. Okay. Okay, I left a negative sign here and a negative sign here. Okay. So, that is the coming from the bending equation, you get that sigma xx at x is minus mz by izz to y minus y naught, and here it is x plus delta x by izz into y minus y naught. Okay. Now, substituting, what I want to find next is I want to find the net compressive force acting on this face, net compressive force acting on this face. That is, I want to find the net compressive force on this face and this face. Okay. F x at x plus delta x and f x at x due to this cut. Okay. Now, what will f x be? fx at x would be integral sigma xx into dA, right, multiplied by dA into a of x. So, this is nothing but mz at x divided by izz, which is a constant, into integral y minus y naught dA. Okay. Similarly, fx at x plus delta x would be mz at x plus delta x. This is a function of x independent of dAx, which is integration with respect to y and z. So, this will be izz integral y minus y naught dA. Okay. So, that will be f of x plus delta x. What I am interested is there a difference between these two is what I am interested in. So, I want to find f of x at x plus delta x minus f of x at x. I left a negative sign at both these instances. Okay. So, I am interested in finding this. So, substituting for the bending moment, what I get is, let us say this is delta fx. Okay. Now, I am interested in finding delta fx. Delta fx would be from these equations minus mz at x plus delta x minus mz at x to 1 by izz integral y minus y naught dAx Ax. Okay. From the expression for mz at x plus delta x given here, from the expression for mz plus x plus delta x given here, this can be written as minus dmz by dx 1 by izz integral y minus y naught dAx Ax. Okay. Now, from our equation for the dmz by dx, we find that from the shear force relating the bending moment to the shear force, this is the governing equation for that. From this we can write this as Vy by Izz integral y minus y naught dAx. Okay. Now, that is delta fx. Now, basically now writing the horizontal force equilibrium, what we find is there is this sigma xz acting horizontally like this, the complementary shear stress would act vertically like that on that face. Okay. So, basically now since the horizontal force equilibrium will demand that this delta fx, which is not 0, should be balanced by this shear stress. This shear stress is acting over a area whose length is delta x and whose width is into this plane, which will be the b. Basically, if I have a cross section like this, the shear stress is acting on this plane like this, and hence its width would be this distance b times this distance delta x. Okay. This distance b times this distance delta x. Okay. So, now writing the horizontal force equilibrium, I get it as summation fx equal to 0 would imply that f of x at x minus f of x at x plus delta x minus sigma xy into delta x into b must be equal to 0. Okay. From our expression for delta x, we find that this is nothing but minus Vy by Izz into integral y minus y naught dAx, okay, minus sigma xy delta x b must be equal to 0. From here I get sigma xy to be minus Vy by Izz into b. I left delta x here, delta x there. So, now this will be delta x here. So, this will be minus Vy by Izz into b into integral y minus y naught dAx Ax. Okay. Okay. Now let us understand what this term integral y minus y naught dAx is. Say I have a cross section, I have some arbitrary cross section. Okay. I segmented it at some distance y, the coordinate system is y and z. I segmented it at some distance, segmented it at some distance y, I segmented it at some distance y. Okay. And y naught is this location of the neutral axis, which I am assuming that I am at the neutral axis location. So, y naught is the center, this is y naught, that is y naught comma z naught, or I am taking it as a origin. So, this will be 0 comma 0. Okay. So, that is y. So, this is nothing but the centroid of this area, it is this hatched areas CG of the shaded area is say ys, then this integral would be minus Vy by Izz into B into ys into As, where ys is the shaded area, As is the shaded area and ys is the center of the shaded area. Okay. Now, why is this negative sign there? This negative sign tells us that the sigma xy is a reaction to the applied shear force. Okay, the shear force is arising at a section. So, and in shear we saw that a direction does not matter whether it shears like this or whether it shears like this, essentially the conditions remain the same and hence we can draw the negative sign. Okay, in shear the direction does not matter whether it shears like this or whether it shears like this, the criteria remains the same and hence you can draw the negative sign, and in general write sigma xy as Vy by Izz into B into ys to As, which is the centroid of the shaded area and As is the area of the shaded area, or this is Vy by Izz into B into integral y minus y naught dAx Ax. Okay. So, that is the expression to find the sigma xy. Okay. Now, let us move ahead and compute sigma xy for a rectangular section. Okay. So, let us say I have a rectangular section. Okay. Now, let us say that is y and that is z, that is y and this is z. Okay. Now, I have to compute, get a section somewhere in between and get the area of this section, area above that section point, and I have to find the CG of that area. Okay. So, what is As? As, if this width is B, depth is h, the centroid would be at a distance h by 2. Okay. So, area of the shaded region would be h by 2 minus y into B, okay, where this distance is h by 2, this distance is y, and hence this distance would be h by 2 minus y times the width of the cross section gives us the area of the shaded region. Okay. Now, I want to find ys, I want to find ys, that is the centroid of this shaded region, this centroid would be y plus half of the thickness of that section, okay, which will be h by 2 minus y into 1 half. So, this will be h by 2 plus y into 1 half. Okay. So, now what is the shear stress? Sigma xy from our previous expression is Vy by IZZ into B, okay, where B is the width of the section at the location where you are finding the shear stress, into YS into AS. So, this is going to be Vy into Vy by IZZ into B into YS is 1 by 2 H by 2 plus Y into AS is H by 2 minus Y into B, that is sigma xy is Vy by IZZ into B into H square by 4 minus Y square into 1 by 2. Okay. Now, let us substitute for IZZ, this will be Vy by B H cube into H square by 4 minus Y square 2 by 12. Okay. Let us substitute for IZZ, it will now be this expression in here. So, this will be 6 Vy by B H into 1 by 4 minus Y by H the whole square. Okay. So, you got the expression for sigma xz as 6 Vy by Bh into 1 by 4 minus Y by H the whole square. Okay. Now, where will the maximum of this occur? Maximum of this, from differentiating this with respect to y and equating to 0, you can see that maximum of sigma xy occurs when y is equal to 0. Okay, that is the neutral axis location, because you have chosen the coordinate system to be coinciding with the neutral axis. Okay, 0, and this maximum sigma xy maximum is 1 by 4 into 6 Vy by Bh, that is 3 by 2 Vy by Bh, that is 3 by 2 sigma xy average. Vy is the shear force, B by Bh gives you the average shear stress acting on the section. Okay. Now, you find that the maximum shear stress is nearly 50% more than the average shear stress. Okay. So, that is why you have to do a rigorous analysis to find what these stresses are. Okay. So, now we found that maximum shear stress is 3 by 2 times sigma xy average. This 50% is for this section, for different sections there will be different percentages of the sigma average that will occur. Okay.